My computer, make the noise. There it goes. We are going to talk about how plate tectonics controls global climate change. I'm not getting into human impact. That is all the way in the 6 weeks. How industry and the massive amounts of carbon dioxide that we do create as human beings affects it. I'm not talking about that today. I'm talking about how the breakup of Pangea has affected it, how volcanic activity affects it, how much ocean or how much land is available at the equator, where the ice caps are, do they or do they not exist? That's what we're talking about today. And I have to hope that all of my stuff animated correctly on my slides, because I did this over a Christmas break, so it's been a while since I've even looked at this one. For the opener, you have to keep in mind it has the word historical in it. What is the single most important historical contributor to global change? Because it is not us. Yeah, it's the motion between where land and ocean is. Ocean, water holds on to heat. Land reflects heat back into space. So depending on how much water or land is available at the equator, which is straight on from the sun, that is the single most important feature of our planet as to how warm it becomes. Yes, there are other factors, especially now since we exist, but historical, it's how much water versus how much land is representing towards low latitude, which is the equator at 0.
So more water on the equator.
Yes. Yes. The more water, that's where we have direct insolation, like straight on rays from the sun. In general, the warmer the planet is going to become. And think about, if you go back to Pangea, was one supercontinent, but the rest of the freaking planet was water.
What was that?
What? I said freaking. I didn't say a bad word. Go back and listen to the video. I did not say a bad word. No, that was a. Anyways, hush. I have to say ISS and not whatever. You were coughing. Okay. So, plate tectonics, how Pangea has broken apart and how our continents have moved, has controlled how much land versus how much water is representative towards the equator. And honestly, that's the single most important contributing factor to how warm our planet becomes. We are ignoring human beings and industry right now because, yes, there is an effect that we have on it. I will tackle that debacle in the 6 weeks. I'm not doing that one right now. So 5 major ways that our planet has its climate affected. So plate tectonics is what we're focusing on today, which will include the motion of ocean currents, which will also include how active volcanoes are, the orbit and the tilt. Now, I'm going to save that one, I think, until next 6 weeks. And I don't know how mathematical I'm going to ask you to do this, but our planet, right now, our orbit is actually more circular. We know it's an ellipse, okay, but it sort of stretches and condenses like taffy over a period of about 100,000 years. And sometimes it's more stretched, more oval shaped than it is right now. And when that happens, you have longer periods of cold. So you have more extreme swings. We're not doing that right now. I don't know how in depth, I could be really mean there. I don't know how in depth I'm going to be when we do orbit and tilt. And right now, our poles, our north and south pole are wobbling really bad. So we'll see how much I go into that. But that was going to be pushed back until at least next 6 weeks.
How did people come up with leap year?
Leap year?
Yeah.
Okay, because we go around the sun not every 365 days, but every 365.24 days. So there's a reason why leap year's every 4 years, right?
Mm-hmm.
But it's not on turn of the century. So at 2000, we didn't have one. And in 2100, we're not going to have one. Because it's not exactly, if it was 365.25, then we would, but we don't. In fact, This year, they're talking about doing a negative leap second for the atomic clock, which is the first time ever that that's occurred. I don't know if I mentioned that in this class or not. Normally, we have to add a second to the atomic clock to fix it. That's a really good question. I'm not an astrophysicist. I'll have to look it up. I'm sure it has to do with markers that we have between stars and historical data. I'm sure it does. I just don't know specifically what it is. But yeah, they're talking about actually removing a second from the atomic clock instead of adding a leap second to the atomic clock.
So a leap second is a day?
A leap second is a second for the entire clock. 1 second, not a day, a second. I'm not in charge of the atomic clock, so. But then we also have greenhouse gases. Now, greenhouse gases can be emitted from volcanoes, which is the one that we're going to specifically be talking about today. But greenhouse gases, carbon dioxide, sulfur dioxide, methane gas, technically water, these things do affect the temperature of our planet. Like I said, we're just not going into the human aspect yet. We'll do that later. Okay, so this is what you said. Plate tectonics, they affect how much ocean is present. And depending on if you have one big blocky supercontinent versus space in between them, that affects the currents of the ocean. The Gulf Stream is like the primary contributing factor to the temperature and the weather on our planet. You've ever seen Finding Nemo when the turtles go into the Gulf Stream and then they sort of shoot along? That's the Gulf Stream. Well, water has what's called a high specific heat, which means it takes a lot of energy to heat it up, but it also takes a lot of time in order to remove said energy and put it, let's just say, into the atmosphere. So it's sort of like a temperature regulator. It's like a thermostat on our planet. Is the ocean or just water in general. It doesn't have to be seawater, just water in general. That's why if you live close to the ocean, you tend to have lower fluctuations between day and night. But if you live in Arizona in the desert, you can have literal 80-degree temperature swings between the day and the night because there's less water. It's like a thermostat. The Gulf Stream affects the jet stream, which is your atmospheric flow. Like I said, the oceans control our weather. They control which way your generic weather patterns are going to flow. And in our country, they tend to go from west to east, and they also tend to go from north to south. And we have a nice cool front that came through the last couple days. Glaciers are made of ice. That's not an aha moment for y'all. But they have what is called higher albedo. Albedo means it reflects sunlight back into space. And so it doesn't get absorbed by the planet, it just gets kicked back into space. Like, I don't want you. If any of you have ever been skiing and you did not put on suntan lotion and you've gotten what we call snow burn or wind burn on top of it, you know that even though it's cold as snot outside, the sun hits the snow and it reflects back up to you and you get horrible sunburn right here and underneath the nose because it's reflective. Volcanic activity. More volcanic activity increases temperature. Lower volcanic activity in relationship is going to reduce temperature because of the aerosols, the chemicals that they spit out into the atmosphere. Now, you go back to ancient times, and it's anywhere from 8 to 15 degrees Celsius warmer than it is today. 20 degrees Celsius is worth 70 degrees, if that puts it into perspective. It was a lot hotter than it was now, which means that we didn't have any major polar ice. There weren't any continents at the poles, for that matter. Everything was concentrated towards the center, towards the equator. So the most important duo of controlling our climate is the relationship between how much ocean water and how much land is present at what we call low latitude, which means zero, which is the equator. If there's more water towards the equator, we tend to have a warmer planet. If there's more land toward the equator, we tend to have a cooler planet. This shows our current oceanic streams. I'm probably going to go way more in depth with this next 6 weeks. I think technically Earth's changing surface is this 6 weeks, but because I'm having to finish plate tectonics from last 6 weeks, everything's sort of getting shoved forward by about 2 weeks worth of time. The red is warmer water and the blue is cooler water. I did not put a lot of images in the canvas. I don't think I put any images in the canvas on this one. But this is the way that temperatures flow in our current makeup of our planet. Is all of this going to change eventually? Yes. It has constantly been changing, which is why we keep getting warmer periods and cooler periods. One of the reasons why we had a mass extinction at the end of the Permian, which wiped out about 85% of all life on this planet. Pangea broke up. It changed the temperature of the planet. Things didn't survive very well. Okay, so the supercontinent was Pangea. The superocean was Panthalassa, which is probably the one that you did not know, but we covered that sometime last week. I don't remember what day it was. I think it was Wednesday. But this massive continent is Pangea. This massive continent first it broke into two, Gondwanaland and Laurasia. Okay, and then those broke up into other little bits. And you don't have to know those terms yet. I will hit that next week when we talk about the actual breakup of Pangea. What was the order of events? When did we have snowball Earth? Like what were the major things that occurred to our planet that we know of as time went on? But eventually it broke up into the 7 continents that we have now. As land moved, Pangea was more towards the equator. As they started to separate and then move towards the poles, we started getting what we call polar glacial ice. And as we started to form ice, as it went towards higher latitudes, which actually get more indirect insolation from the sun, which means less direct rays from the sun, is what that means in English. They were cooler, allowed the formation of ice. The ice reflected even more of it back into space, which meant that the Earth actually got even colder. Now we're in an opposite trend right now. We're in a warming trend. We're coming out of the last ice age. We're still in the early stages of coming out of the last ice age. Now this has happened over and over and over again, way before human beings existed. Dinosaurs did not drive cars and they were not lighting fires. No, not the no, seriously. So, and I go more into how the snow albedo effect. Like I said, albedo just means to reflect. It is a positive feedback mechanism. We will eventually, when we get into global climate change, like the real section in the 6 weeks that includes people, there are positive systems and there are negative systems. Positive means it keeps increasing whichever direction it's going. In this case, when everything split and we had an increase of ice, which reflected more light, more ice meant a colder planet. Right now we're in the opposite trend where we tend to have a warming, which is making, as far as the poles are concerned, it's not as exaggerated as they lead you to believe, but we still are in a warming trend. And warming begets warming. Cooling begets cooling. But this particular motion, and I know they can't see me pointing on the screen, but this particular motion allowed the ice caps to occur, had a massive decrease in temperature at this particular time, which is the end of the Permian. Well, actually, this was the end of, the Permian was the first one, and then we had another one at the end of the Cretaceous, and that was the last major ice age that we're still coming out of. That one ended about 18,000 years ago. We're still coming out of it. How this works. First of all, it's a positive feedback mechanism, which I didn't put here. It just means if you have more of a cold thing that's forming, it's going to get cold. You have more of a warm thing, which means less ice, it's going to get warm. It's going to reinforce itself. Because ice and land are more reflective. Okay? More land on the equator reflects more light back out into space. Light meaning sun rays, insolation. Even if snow is towards the poles, where we have more indirect insolation, it's still going to reflect it back, which means that the Earth will not absorb said heat from the sun, and it cools. Okay, that is what happened. That's what this bottom one, that is what happened when Pangea broke up. With us right now, because we have more ocean on the equator in relationship to before that is spread out, it is helping to increase the temperature of our planet, which is having a melting trend on the poles. I'm sure you guys have heard about the poor polar bears and you've seen the documentaries, and it doesn't matter who's done the documentary. At the end, it's always global warming, human impact, everything's going to die. It seems the way that all of those documentaries always end. Yes, we are in a warming trend. It's time. We're still in a warming trend. We've been in a warming trend for over 18,000 years. I will show you it looks almost like an EKG that shows you warm and cooling trends. And it shows you how that relates to the isotopes of oxygen that are present in the air, how much methane is present in the air, and how much carbon dioxide is present in the air. They're all correspond to each other. I don't think there's any words on here I need to, besides the snow albedo. No, I didn't even say insolation. Incoming solar radiation is called insolation. If you see that word, what's the matter? What's the question?
Isn't there like supposed to be like some kind of ice age?
We just had one not too long ago. It ended in the mid-1800s. We're going to talk about it here in just a second. We will have, I haven't built the stuff for next, my grammar bad. I haven't built the stuff for next 6 weeks, but we will have at least one day specifically on the massive ice ages that we've had, including the most recent one, which we call the Little Ice Age. We'll have a lesson on glaciers. We'll have a lesson on volcanoes. I just haven't gotten that far in advance. I didn't. Over the break, I got through this week. I wanted to get through the entire 6 weeks, and yeah, that was biting off way more than I could chew. Ocean water in general, doesn't have to be seawater, it can be fresh water. Water absorbs heat. Like I said, it has what we call a high specific heat. That is a chemistry phrase. You should have learned, if not last year, maybe the year before. So it holds on to heat. It will release it, but it takes a lot more time for water to release it. Whereas land, especially if it's covered in ice, tends to reflect heat. We have more insolation, which is a term back from, I want to say it was the first 6 weeks. Insolation means incoming solar radiation. So incoming waves, radiation from the sun. The Earth gets more direct rays at the equator, which is a low latitude. That means zero. The equator is at 0 latitude. It still gets it at the poles, but it's not dead on. It's more of an angle. And so basically it tries to bounce off. It's more of a reflective property, let alone the fact that snow is reflective to begin with. More solid land around the equator begets a cooler planet. More water around the equator begets a warmer planet. And eventually, according to plate tectonics, moving it somewhere around an inch a year, give or take, the mid-Atlantic ridge is going to end up pushing everything back to the other side of the planet, and they'll smash back into another supercontinent. According to plate tectonics, we won't be around to see it. We'll be way extinct before then. In fact, the planet, it may take so much time that we've either our sun is red gianted, or we've merged with Andromeda, or we've been slammed in by another massive asteroid at that time. The human beings will not be here. Cockroaches might. Cockroaches survive everything. Y'all, they live for 7 days without their pen.
I see.
They don't need to. They don't. I don't. Y'all, cockroaches are weird. They've been around for a really long time. All right, now we're going to specifically talk about volcanic activity. We know when we have subduction zones, that's where we have more volcanic activity. That's what causes the ring of fire around the Pacific plate. Where you have the oceanic Pacific that's subducting underneath the various continental plates that are surrounding it. More volcanoes, more volcanic activity means that they're going to spit out more of these greenhouse gases.
No.
I don't know. It could be scheduled related. I mean,
Pretty sure that's what it is.
so okay. One of the major greenhouse gases, let me just say it that way, is carbon dioxide. There are others. Methane gas is one of them. Sulfur dioxide gas is another. Okay, but the one that they like to focus on is carbon dioxide gas. And that is one of the ones that volcanoes spit out. When Pinatubo erupted not too terribly long ago, it reduced global temperature by about 0.5 degrees Celsius, which doesn't sound like a lot, but y'all did it to the entire planet. One volcanic eruption. Put that much stuff up into space. All of the aerosols, okay, not just carbon dioxide, all of the things that they spit out, including water vapor, they block light. They go up into the atmosphere, they get in the way, they essentially cause a shadow. The light can't come through, like a thick cloud, whether it's toxic or not, which means less light reaches the surface, which means temperature goes down. I am not talking about complete nuclear winter at this point. It's just there's stuff that's put into our atmosphere that blocks our sunlight. Now, when you have monstrous eruptions, like when Yellowstone goes, if it's the big one, when that one blows up, that's going to have a more increased cooling for a longer period of time, but it's not necessarily going to like wipe out all life on the planet. Not necessarily. Anything that's super sensitive is going to be affected, but it's not going to be like 1,000-year-long, like no sun kind of event. As long as it doesn't go completely up into the stratosphere. If it goes up to the stratosphere, then we have more of a problem because there's no weather in the stratosphere and it can't be rained out. That is my big concern about the major eruptions that we can have. Oh, there is one more on here. Okay, so a normal volcanic eruption, just a generic eruption, nothing catastrophic. So we're not talking about Yellowstone going kablow. Like a Kilauea or a Mauna Loa, the Hawaiian ones that blow up all the time, that spit stuff out all the time. A normal volcanic eruption only puts out about 1% of what we do with industry. We put a lot of carbon dioxide into the atmosphere. We do. Now, without carbon dioxide, plants will suffocate. Now, I'm not saying pollute. I'm not saying that. There's a balance, the carbon cycle. There's a balance between plant life and animal life, which we're, well, I know you don't want to think of human beings as being animals, but we're in the animal kingdom. But we, because of industry, because of burning fossil fuels, we produce a lot more carbon dioxide as a whole, as opposed to normal volcanic activity, not extreme volcanic activity. I'm not saying humans bad, but our country actually has a lot of regulations to help curb our carbon footprint. Countries like China, they don't care. They just pollute like crazy. Pass. They say 12, yeah. I would suggest a-hole.
They're all long.
I know they're all lot, but I would try a-hole first. And if that's not working, I would try like over in the mall area.
It's the only bathroom that we can come off.
Okay. Oh, what did I do? I pushed the wrong button. I apologize. There we go. Mountains. This is still plate tectonics. We have two converging continental plates. They cannot subduct. The only thing they can do is go up. They buckle up to make mountain ranges. And I know we don't really have any mountains around here. But if you fly over mountains, you're going to notice if you're going westward, let's say you're going towards, let's say you're flying into California, flying into LAX. As you're going towards the mountains, you notice it's like arid, like it's dry. But as soon as you go over the mountains, it's extremely lush. There's plants everywhere. That has to do with how moisture accumulates as it goes across the mountain. Now, like I said, our jet stream goes from west to east. So the windward side from the ocean carries moisture. And as it starts to go up the mountain peak, that moisture condenses and it rains. And therefore you have a more lush environment. Lush just means more plants. Well, it rains itself out. But when it goes over the mountain, all that moisture is gone. And so you tend to have a more arid or desert-like dry environment on the leeward side. So for our mountains, for the Rockies, which is what I'm specifically talking about, the windward side is coming off the ocean. Okay, so heading east, it goes over the Rockies, and then the eastern side of the mountains, which have less moisture, the leeward side, they tend to be more arid and have more of a desert-like environment. It's like a microcosm of climate when it comes to mountains. Windward, coming off the ocean, leeward as it crosses over the peak, or the spine is the right phrase if it's a mountain range, the backbone of a mountain range. Okay, now we're going to get into a lot more technical stuff. We look at three things to go back in time to understand if it was a warmer environment or a cooler environment. We don't necessarily know the exact temperature, but we can tell if it was warmer or cooler. We look at pores in the ocean floor, and we look at the isotope composition in the sediment itself, in the rock itself. We look at calcium carbonate, that's shelled creatures like snails and corals and stuff like that. That carbonate, carbon dioxide, carbonate is CO3. That carbon dioxide is absorbed. The oxygen and the carbon dioxide is absorbed to help make carbonate. And we can analyze what's present in there. These are very sensitive critters as to, was it warmer or cooler? Specific pollens. Certain plants only grow in extremely warm times. Some like to grow in cooler climates. So we can analyze what type of pollen's present. Ice cores, specifically Greenland and Antarctica. I can say that really easily. I can't even say that well. We look at oxygen isotopes in ice. We look at how much oxygen 16 versus oxygen 18 is present. I'm not going to make you guys do a chemistry lesson, but oxygen normally has a mass of 16. That's what we're breathing right now. There's a heavier isotope of oxygen, which is oxygen 18, has 2 more neutrons. Oxygen 18 in ice means it was a warmer temperature. More oxygen 16 means it's a cooler temperature, which is what we're doing right now. Like I said, we're coming out of our ice age. And then we're going to go back to looking at tree rings. This was something that we mentioned a while ago. How close together are the rings? Closer is cooler, is stunted growth. Further apart is accelerated growth, which is warmer. These are the 3 major things that we analyze to figure out, okay, are we dealing with a warmer climate or a cooler climate? And I'm about to go into depth. Tree rings first. Tree rings, you've mentioned this before, go back about 17,000 years, and that's it. They're not good for after that. The closer they are, the cooler it is. The further spread out they are, the warmer it is. We will have a lesson on ice ages, but I am going to talk about the little ice age, which we just came out of. It went through the middle of the 1800s. There's a couple things that happened. The documentary that we watch tomorrow was a major proponent of this. When Loki erupted in Iceland, it erupted for 8 solid months. And it had massive implications on our planet's climate. Okay, thanks. Okay, so I forget where I was just talking about. Okay, so the Little Ice Age, we had this massive eruption. Loki erupted in the late 1700s. Loki actually caused the French Revolution, believe it or not. A volcano caused the French Revolution. But this ice age, which we're just now coming out of, and I've mentioned this before, in various classes, I don't know if I did in here, it's why the Germans drink beer, and it's why the Italians and the French drink wine, because that glacier sheet went so far south where it affected Germany, it didn't quite go south enough to affect the grapes that were a little further south. The barley and the hops, which makes beer, it survived the cold weather in Germany, which is why Germans drink beer. In fact, it's actually part of their meal. Like it's a caloric intake. It's like bread for them. They drink it all the time, but not that they're like rolling around drunk in the street. Like it's part of their meal. But with further south, the grapes survived, and so they tend to prefer wine. It literally was caused by an ice age. The Stradivarius violin, the forests that were affected over this long period of time, because the growth was stunted, it was more dense and it had a better resonating quality, which created those particular violins. If you're not a music person, you don't even know what the heck Stradivarius is. Extremely expensive if you can get one. My late husband's mother-in-law actually has one. Still has the catgut strings on it too, which is disgusting, but it does. Ice cores. Okay, so tree rings went back about 17,000 years, which is great, but that's not a super long time ago. That goes back to the most recent end of the ice age. That's it. Ice cores go back over 150,000 years. We analyzed the percent composition of regular oxygen, which is oxygen 16. That's what this means. O16. Oxygen that has a mass of 16 has 8 protons and 8 neutrons, versus oxygen 18, which is a heavier isotope, which still has 8 protons but has 10 neutrons. Like I said, I'm not gonna. You guys have already had chemistry, but that's what these letters and numbers mean. In ice, not sediment. Okay, in ice, the heavier isotope is indicative of a warmer temperature. The normal isotope, which is what we are breathing right now, is indicative of a cooler temperature. And like I said, we're technically still coming out of an ice age. The other 2 major gases that we analyze in an ice core, whether it be, no matter where they yank the ice from, are carbon dioxide gas, which is CO2, and methane gas, which is CH4. So the isotopes of oxygen, carbon dioxide, and methane, their relationships let us know if we were dealing with a much warmer, or like we are right now, we're dealing with a cooler climate. This shows you the relationship between them. Go away thing. So thousands of years ago, we're right here in a warming trend. Okay, but we've had multiple coolings, warmings, coolings, warmings, and it's planet wide. And some of these lines, some of it is carbon dioxide, some of it is methane. But they do the same thing. They are related to each other. If you have higher levels of methane, you're going to have higher levels of carbon dioxide as well. They go hand in hand. No, you don't have to be able to read that chart. So glacial ice is less than 1 million years ago. So to go super far back, we dig into the ocean floor. We go into the sediment. We go into the preserved records. And the big indicator is coral. But we analyze the different layers of sediment, and we know as we go down, we go further back in time. Whoops. There was one more, but there's not. We're also going to analyze oxygen isotopes, but it's actually the opposite in sediment as it is in an ice core. The specific organism that we do look at, which I think is on the next slide, is coral. Coral is the leftover skeletal remains. Well, depends if it's living coral or not. In this case, it's not alive anymore. But that calcium carbonate, it holds a record of the specific isotopes of oxygen that were locked into the shells of the organism. They grow their own shell, their own external backbone, if you will. Light oxygen, oxygen 16, the stuff that we're breathing right now, all times in the ocean, in ocean water, evaporates. So polar times actually have more of the heavier isotope, oxygen 18, and have less of the lighter S isotope, which is oxygen 16. If it's in a warmer time, it's going to have a higher concentration of oxygen 16 in relationship to the concentration of oxygen 18. Whoops. There was one more on there too. I need to like open up my things. We got one more page about corals, and then yes. We're almost done. Like I said, the things that are growing their shells, they are absorbing whichever prevalent oxygen is there as they're building their calcium carbonate shell, their external skeleton. Corals are extremely sensitive critters. Okay, we have a massive coral die-off going on right now. The Great Barrier Reef is seeing a huge problem with its coral life. Very, very, very delicate while coral is alive. Now, obviously, it's going to trap these isotopes, these two specific isotopes of oxygen, and if they die, then they're still going to be there. And we can go back and we can analyze what is prevalent to figure out, going back in time, going further down into the earth, where we're dealing with a warmer temperature, which would have a specific isotope of oxygen, or we're dealing with a cooler temperature. Cooler temperatures have the heavier, and the warmer temperatures have the lighter isotope. So this is the one that is extremely accurate over millions of years. Now, if you're talking about like billions of years, you're getting into different isotopes that I don't have the time to get into all of those today. Now, when we do evolution, I probably will, but I don't have enough time to get into it right now. And this is the last section for the test. That's Friday, but the documentary tomorrow on Iceland. As soon as you guys get in here, I have to start it. It is 45 minutes long. The assignment is chronological, like the worksheet that goes with it, and I'll print them out. If you want to do it on paper, or if you want to follow along from Canvas, it does not matter to me. But there are questions on the test specifically about how Iceland functions. Because Iceland is different than most other geological areas for a couple of different reasons. Let me check. Here's my grade book. Okay, let me double check attendance online. Pause the recording so they don't hear me. Yes, this is the last bit.